Welcome. So today we're going to look at the problem solving session for section I, and it's mainly about resistance and there's a bit on power. So let's have a look at it. It says, first question, write the equation that links the resistance of the resistor R with its length L, cross-sectional area A, and resistivity ρ. Now, don't need to give you those letters, you can just use the words. Ideally, you have that equation in your brain. I still prefer to write down what the letters are. R is resistance. I don't need to write that down. For me, I'd write down R, ρ, L, and A as I'm reading the thing. And that's jogging my memory. I like visualization. I like to understand what's going on. So here's my resistor. It's a piece of graphite and it has a certain length, and if you make it longer it's more resistive. That means that L should be on top, and if you make the area wider it should be less resistive because there's more paths for the current to go through, so A should be on the bottom. And then there's the material property, and that is your resistivity, and that's ρ. And the bigger the resistivity, the bigger the resistance of the example. So ρ should go on top. So even if I didn't remember the equation, I could kind of figure out this general form. The danger is you would not get any coefficients like a half in a half mv squared, and you wouldn't get any weird things like epsilon naught if an epsilon naught was in there. So it's best to know the equation. And what I say is people get resistance R and resistivity ρ mixed up. And resistance is about a sample. That sample has a certain resistance. Whereas the material that sample is made out of, that graphite, that material has a certain resistivity. So the material has resistivity, but the sample has a resistance. And this is just like, you know, an object can have a mass. This sample of matter has a mass, but this type of material has a resistivity. So two words sound similar, but they're kind of different. A bit like mass and resistivity, mass and density. I hope I didn't. I hope I said that right. This sample has a certain mass. This material has a certain density. I think I said that wrong. Let's go to the next one. In this next one, what we have is this type of problem causes issues because it's a bit of an abstraction. It says, consider a cylindrical sample of resistive material. Which trace best represents the resistor's resistance on a vertical axis versus the resistor's radius horizontally? And so we have, here's my visualization. It's a cylinder. I have a certain length of resistor material. I have a certain area. It's cylindrical, so it's got a certain radius. And then there's a certain density of the material. And my equation is resistance is equal to, or R is equal to ρ L over A. My resistance is equal to my resistivity times my length over my area. And you can tell if you make it longer, there should be more resistance. If you make the area wider, there should be less resistance because there's more paths. And if you change the material to a more resistive material, then I expect the resistance to go up. So that makes sense. It doesn't answer my question though, because I'm not plotting against area, I'm plotting against radius. So I've got to do this extra step. And I say, well, that's a circle, so we have pi r squared for the area. So I substitute in, and then I say, this is where it gets tricky. My advice is you look at the axes really carefully, and it says that resistance is vertically, so I coloured that in red, and I coloured this letter in red, so I realised that's the same. What's on the graph in one point is part of my equation. And then you look at the other side and you say, well, that's resistance, so you find resistance on your equation, and it's not the squared, it's just the R. So that's one of the mistakes that people make, is they think that the squared is attached to the R, and that's what you're plotting. And you're not, you're only plotting the R. Because this is what's going on, this is a bit of explanation here. If I plotted the resistance versus the radius, I get an inverse square relationship, because if I look at this equation, the radius is on the bottom, so it's inverse, and it's squared. So the graph of resistance versus the radius should be an inverse square. If, on the other hand, I plotted the resistance versus the radius squared, then it would be an inverse relationship, because the R squared is on the bottom, and it is what it is. And then the third thing, and we did this in lab, I think, is if we plotted R versus 1 over R squared. Well, 1 over R squared is just something on the right-hand side, so that's linear. So I can get at least 3 graphs out of this relationship, just with these 2 parameters in various forms. So you got to watch your P's and Q's. You got to be careful with this. The relationship is a curvy one going through a dip. So whether we think it's the first one, the inverse square, or whether we think it's the second one, the inverse, I've only got one thing to show it in the current form of these questions. So it's A. That's a limitation of my questioning. I should be able to do 2 graphs, one's an inverse square, so you can tell the difference and test you on that, but I've just never got around to it. So you could make a mistake and think it's an inverse and still get the right answer on this one. Just my problem with question asking. I put a note here and I say, if you cannot spot the relationship, if you can't look at that and say that's an inverse square, then what do? And the answer is you make a graph. And the trick with making a graph is you look at your equation, and anything you don't want to mess with, you call 1. So the rho L over pi is 1. Just forget it, it's 1. And then you just make columns and you go, well, I'm changing little r, so I'm changing the radius, make a column for that. You know, it has to be squared, so make a column for that. And then, well, actually it's 1 over r squared, so make a column for that. And because this rho L over pi is 1, 1 over r squared times 1 is equal to big R. So I make my columns, and then I say, well, what would happen if little r, the radius, was equal to 1? Well, if radius was equal to 1, then r squared would equal 1 times 1, which is 1. And 1 over r squared, which equals 1 over 1, which is 1. So my answer r would equal 1. And what if it was 2? Well, r squared is equal to 4, so put down 4. 1 over r squared is equal to 1/4. You don't have to work out the decimal. So the answer is 1/4. And if it was r equals 4, r squared equals 16. 1 over r squared equals 1 over 16, which means the answer is 1 over 16. Now that's assuming that, you know, the middle bit, rho L over pi equals 1. It's like I'm taking liberties here. But if I look and I plot this thing out, my r goes from 0 to 4, and my big R, my resistance, goes from 0 to 1. And I plot this thing out and I go, it's when little r equals 1, the resistance equals 1. When the radius equals 2, the resistance equals 1/4. And then when the radius equals 4, the resistance equals 1/16. So it's got that steep curve. That's an inverse square. If it was an inverse, then it would be 1 and 1 again. But then the second point would be when when the radius equals 2, the resistance equals 1/2. And when the radius equals 4, the resistance equals 1/4. So you can see there's this different curvy line. It looks, curves are curves. It looks similar, but it's actually quite different. So, either way, you got to recognize that that's A. And some people can look at, I know it's annoying, some people can look at it and just do it, and other people, it's like pulling skin, you got to do it. But you can do it. Next one. This is a question on the temperature coefficients. So resistivity is caused by the movement of the atoms inside the material going so quickly that it actually appears to have a bigger cross-sectional area than it should have. So the time it takes to pass, it's the time it takes for the electron to pass, there's a good chance it's going to get hit. And if we increase the temperature, because this thing's moving around more, there's much more chance it's going to hit. And so it's going to be more resistive. It's like trying to run through a crowd of people who are stationary versus trying to run through a crowd of people who are moving backwards and forwards versus trying to run through a crowd of people who are just going crazy. If they're going crazy, you're going to hit more of them. That's what's going on here. So what we find is that there's a temperature-dependent effect for resistance. So at standard temperature, which is 20 degrees C for some reason, we found that there was 14 ohms of resistance in this sample. But then when we heated the sample to 32 ohms of resistance, at 32 degrees C, we got 46 ohms of resistance. So I make my list. R0 equals 14, T0 equals 20, R equals 46, T equals 32. Now notice I didn't use those symbols in the wording. So you got to know the context to get the right nomenclature to jog your memory. And the equation is that the final resistance is equal to the standard resistance, bracket 1 plus alpha, there's your coefficient of friction, coefficient of resistivity, parentheses T minus T naught. I have trouble remembering this equation. And so I help myself. It's not, we're not in Harry Potter. It's not, I mean, you should learn the equations, but the equations do come from some logic. And here's the logic. So what happens is a resistor will increase with temperature. And so if I imagine plotting a graph of temperature versus resistance versus temperature, I find that when temperature is T0, we get R0 for our temperature. And when temperature is increased to T, I get R for my temperature, for my resistance. This is a straight line, so there's a slope to it. And what I can say is that my final resistance R must equal wherever I began, R0, and then it's going to be plus, it's going to be the slope times this temperature interval. So it's alpha T minus T naught. And I find that a little bit more sorry, my family just came home. So R equals R0, 1 plus alpha T minus T naught. Sometimes in math you're taught to rearrange the equation to isolate the thing you want, but what you find in physics sometimes is it's best to put the numbers in first because things cancel. So we put in 46 equals 14, bracket 1 plus alpha, parentheses 32 minus 20. So the 32 minus 20 simplifies to 12. And then we have 46 equals 14 plus 14 times 12 is 168 alpha. And then rearrange. I like to write down every step I don't like to do things in my head, because even writing down every step, sometimes you can make slips, but if you jump steps, you will make more slips. And that simplifies out to something like 0.19. Now, is this just a coefficient, or has it got units? It's actually got units, and the units are not so easy to see. If I imagine the r being divided by another r, because I take it to the other side, then that is dimensionless, and so the alpha is left by itself when the temperature goes to the other side and divides. So the temperature terms are multiplying on this side, so when they go to the other side they'll divide. So the units are 1 over degree C. This is basically saying you'll get 0.19 times per degree C. Okay, let's try this last, or I'm sorry, I've got to stop again and rearrange things. Hold on. So here's the last question. So a 14 amp current flows through a resistor when an 8 volt potential difference is applied across its ends. How much power is dissipated by the wire? So the resistor works by getting in the way of the flowing electrons. They collide, and it's a collision. So there's going to be there's energy given off. There's not always energy given off, but in this case there's energy given off, and that's given off as heat, and you feel resistors get warm, and so that energy is dissipated. We say it's dissipated in the resistor, and the power is a measure of energy per second, or work done per second. It's the rate at which energy is spent or transferred or work is done. Okay, so the equation is power is equal to I delta V. My I is 14 amps, my delta V is 8 volts, my P is my power. A few things. I'm actually pointing out my own slackness here. So if you notice, I have my my battery symbol, I have my resistor symbol, that's the international symbol. I have my current flowing from positive to negative, and then I said delta V is over here. Delta V is a change in voltage, a difference in voltage, and that's appropriate. There's only one component in this circuit, so that there's the battery and then one component. So whatever voltage drop I create across the battery is dropped across this resistor. So yes, in the end, if there's delta V across the resistor, there was delta V made by the battery. But better terminology is to say that the battery produces an EMF, electromotive force, of a certain value, and that the potential difference of 14 volts occurs across the resistor. And what I say is, of 8 volts occurs across the resistor when a 8 volt potential difference is applied across its ends. Now, if I had more than one component, then my EMF would not be 8 volts. It would be, in order to have 8 volts there, I'd have to have a bigger EMF. So I need to tighten up a little bit on EMFs and potential differences. But people tend to interchange. It's just common language, and once you're comfortable with these things, you can interpret both ways. So just a point on that. Now, the equation you got to know is that power is equal to the current times my potential difference. And if I look at units, I know that my potential difference is in volts, which is joules per coulomb. If I can add a pen here, maybe I can. So this might not be the neatest thing out, but this is joules per coulomb. Watch out for your units, man. This pen's not working very well. Joules per coulomb for my voltage, and for my current it's coulombs per second. So this, when I look at it, gives me joules per second, which is power watts. So that works out. So it's 14 times 8, 112 watts. If this was a test question, unless I was looking for a really nice, straightforward test question, I could make it a bit more interesting. I could give you a different EMF with a second component and, you know, just give you more information, basically. I could tell you the temperature and see what you do with it. One way I can also make it more interesting is I don't ask you for the power, but I ask you for the amount of energy dissipated in a certain time. So I could ask for the energy dissipated in 2 minutes. So this question is not answered as well. I've noticed that. The two equations of power is equal to current times the potential difference, and power is equal to the change in energy over the change in time. So my current times my potential difference is equal to my change in energy over my change in time. So my change in energy is equal to my current times my potential difference times my change in time. And the common mistake is that people will put down 2 for 2 minutes when in fact it has to be 120 seconds because we're working in SI units. So that's one common mistake. And the other common mistake is people just get confused. They just don't put these two equations together because they met them in different chapters, and unless they practice it, they don't connect the two. Power is incredibly important. My brother's an electrical engineer, and he said to me once, "You guys, physicists, only care about energy." Whereas, and I said yes, and I thought that was quite insightful of him, because people think we care about forces and velocities and accelerations, because that's the first chapter. But in reality, we can do all that stuff in terms of energy. So the realization over time is it's all about energy. Can the job be done? Can this happen? Can this thing occur? And I said to my brother, "What do you care about?" And he said, "We care about power." And that struck me as very strange because we hardly ever talk about power in physics. And I said, "Why do you care about power?" And he said, "Because energy tells you, can you do this job? Do you have enough energy to achieve this task?" And I nodded. And he said, "But engineers need to know, when can you achieve this task? Is it going to take you a day, or is it going to take you a lifetime?" And for us, it matters because, you know, it's the real world and we've got to complete a job in a certain time. And I just never thought about that. So bear that in mind. Engineers tend to be much more practical than certainly than physicists, in my experience. So it's an interesting insight into the mindset of engineers versus physicists. I've gone on a bit too long, but let's pause it there and I'll see you later. Bye-bye.